So all of the understanding behind the shape that molecules take on can actually be understood in one simple concept. And this concept is highlighted under what's referred to as VSEPR theory. The VSEPR theory just stands for valence shell electron repulsion, or electron pair repulsion. So VSEPR. And all that says is that when we have electrons, whether they're in a bond between two atoms, or whether they're actually even lone pairs of electrons, or even individual electrons, they're going to be shoving on each other because of that Coulombic force that we looked at in terms of Coulomb's law, where we have one charge and another charge, and the force proportional to that charge and the radius between them. So when both of these negative electron groupings are near each other, they're pushing. So what are they going to try to do? They're actually going to try to get as far away from each other as possible. And that's pretty much this entire theory. Farthest possible distance. Okay. So as long as you remember that, you pretty much can figure out all of the rest of this without any memorization almost at all. So what happens if I get two things, and I take those two things and I try to put them as far apart from each other as possible? Well, you can do this with balloons too, and if you take balloons and you tie them together in the center, they'll naturally try and get as far away from each other as possible because the structure of the balloons push on each other. So two things as far away from each other as possible will naturally form a straight line, and this is referred to as linear geometry. And what we're going to talk about here first, all of these shapes are referred to as electron geometry, or electron molecular geometry. Okay. And its electron geometry is a little bit different than what just pure molecular geometry is, which we'll talk about later. But for right now, all of these shapes are electron geometries. So the beryllium, our diagram is in the middle. Chlorines are attached on the outside. 180-degree angle between the two of them, straight line. We name the shape, we call it linear. If we have three things attached to a center, what we end up with when the three things attached to the center get as far away from each other as humanly possible is something called trigonal planar. It's three atoms in a circle, or a triangle, I'm sorry, around a center atom. And the angle between one atom and the next that's attached to the center is 120 degrees. It's 1/3 of 360 degrees of a circle. Now, what I want to point out here is when we name this trigonal planar and we name this one linear, that we've also talked about a different way to name these groupings when we looked at the Lewis dot structures. And the Lewis dot structures of these would be this for beryllium chloride and so all those dots, and these Lewis structures give us the ability, forgot the dots, to name these in terms of our ABN nomenclature. So beryllium chloride, with beryllium's special ability to only need 4 electrons in order to be stable, leads us to an AB2 designation. Boron trifluoride, with its 3 groups attached to the center atom, gives us AB3 designation. All AB3 molecules will be trigonal planar. All AB2 molecules will be linear. As we're already starting to see kind of patterns emerge here in what we call the shapes compared to what we can name them. Now, if we have 4 groups attached, that's referred to as tetrahedral geometry. And something like methane is an example that we'd see a Lewis dot structure of. 4 groups attached to the center. That means AB4. It's our overall shape. And AB4 means I have the carbon in the center, and on each of the edges, each of these vertices outward, I have a hydrogen. And it's a little hard to draw this structure sometimes. You just kind of draw a little bit of a lopsided triangle, take a point to the top, draw down to each of the corners, and then center atom right in the center of the whole mix. Other ones on the vertices. And so we got about 109.5 degree angle between one atom and the next here, which is much different than the Lewis structure showing us, right? The Lewis structure is showing us 90 degrees. That's not the actual shape. That's just the connectivity. So don't forget that. Connectivity is what the Lewis structure gives us, how one thing is connected to another. We then have to take valence shell electron repulsion theory and come up with the idea that methane, CH4 as a molecule, will adopt a tetrahedral arrangement as three-dimensional space. Well, 5 groups, when they try and get as far away from each other as possible, form this like triangle in the center, and something to the top and something to the bottom of it. So there's various molecules that adopt this shape, but the designation that they get in ABN nomenclature is AB5. And an octahedron forms kind of a square, something above, something below, our A in the center, with B's on all of the vertices again. All the angles are 90 degrees except the top to the bottom, or left all the way to the other side. Those are 180, but overall almost all the angles between immediately adjacent atoms will be 90 degrees in an octahedron. Keep in mind, an octahedron is any molecule that has an AB6 designation in its Lewis dot structure. Excellent. So those are the basic groups. We're going to start introducing the groups that have N in them in the next section.